is right here. So we mostly learned how to write and balance chemical reactions in chapter 5 and classify them. We learned lots of different ways to classify them. We could classify them as like these 5 right here, the synthesis or combination, decomp, single, double displacement, or combustion. And then we also learned precipitation, redox, and acid base. So let's remind ourselves, well, actually, before I jump into that, the 2 important tips when you're balancing. I think balancing is relatively easy. There are some equations that are always just challenging, but remember that anything by itself, okay, an element by itself, do it last, because you can put a coefficient in front of it without messing with any other elements. All right, so that's one tip. And then if you have a polyatomic present on both sides, which you'll have the polyatomic ion chart for the exam, you treat it as a single unit. So if you have sulfate on both sides, you don't have to balance the S and the O separately. You can balance it just as units of sulfate. 1 sulfate, 2 sulfates, whatever. Okay, synthesis. That was like this, but it's not just like this. We can have A plus B making AB, okay? But you could also have something like A plus B plus C makes ABC, or AB plus C makes ABC. The gist of this is that reactants are coming together. So you typically, in a combination reaction, you have more reactants and fewer products because something has joined together, if that makes sense, okay? So those are just a few examples of what that would look like. Decomposition, I'm gonna erase so I have room, is the opposite, okay? That's where you have a reactant breaking down into multiple products, okay? So it can be like this, but it doesn't have to just be like this. There are other examples you could think of. If we look at the reverse of this, A, B, C breaks down into A plus B plus C, okay? Here, you have 1 or 2 reactants breaking down into 2 or 3 products, okay? More products. Single displacement, this is where you have a element and a compound, okay? An element and a compound. So we'll express that like this. A being your element plus BC. There's your compound. All right, and then A, depending on what it is, it's either going to be a metal or a non-metal. If it's a metal, look at this compound here. Usually it's an ionic compound. Metals become cations, right? They become positively charged. So here in BC, which one would be your cation? Which one would be your anion? B would be the cation. We always write cations first in an ionic compound, okay? So B would be your cation, so A would replace B. But if A is a non-metal, non-metals like fluorine, chlorine, bromine, they become, or oxygen, they become anions, okay? So if it's a non-metal here, it would replace C. So it just depends on what A is. If it's a metal, it will replace the cation. If it's a non-metal, it will replace the anion, okay? So if it's a metal, we'll just write like this. You would get AC plus B would be by itself. That one's if it's a metal. If it's a non-metal, it would replace C, and you would get BA with C by itself. Okay. Double displacement. This is where you have 2 ionic compounds. So that's where you have like AB plus CD, and the cations and anions switch. Okay, so A and C are your cations, so you'll get CB, and then you'll get AD. What? Yeah. Thought I wrote C and B backwards, but I didn't. All right. Combustion. I think this one's the easiest because you always get the same products. You get some sort of carbohydrate, meaning it's a compound with just carbon and hydrogen, and you don't know what the subscripts are. It could be C2H6, C3H8, C4H10, any sort of carbohydrate, okay? And then it's always going to be reacting with oxygen, always. Oxygen is a reactant here. And then anybody remember what 2 products we make? Yep, carbon dioxide and water. Some sort of carbohydrate, which is the C and H component right there. And it could have any sort of number of subscripts. Could be ethane, methane, butane, whatever. And then oxygen is reacting with that. Make CO2 and water. Those are your only two products. So then the three complex types of chemical reactions that we discussed were precipitation, this is where you have some sort of compound, we'll say A, and it's aqueous. Well, usually I should write it as a compound, right? So AB being aqueous plus CD, and it's aqueous, and then it's like a double displacement reaction, and you make some sort of product. So if these switch and you get AD, let's say that becomes a solid. That's the precipitate. And then CB would be still aqueous. Okay, so you got two aqueous compounds coming together to give you a solid product. And you use your solubility chart, which I'll give you on the final exam. You'll have that solubility chart. Okay, the other one was acid-base. Acid-base neutralization reactions. And we said here you have some sort of acid, HA, and then some sort of metal hydroxide. It could be sodium hydroxide, lithium hydroxide, potassium, any sort of metal hydroxide, potassium hydroxide. And it comes together, I'll highlight the H from the acid and the OH from the base come together, and those make water. And then you get some sort of salt, which is a metal with the anion from the acid. So if you had like HCl and sodium hydroxide, you'd make water and sodium chloride. Now, obviously, we've expanded this definition in chapter 10, but for the sake of classifying, I usually keep it kind of limited to these forms, or that form. And then 3, the last one was redox, everyone's favorite. Okay, so do you guys remember? Did I have? Yeah. Redox is reduction and oxidation. So anybody remember how reduction and oxidation work? How we define those processes? That has to do with finding oxidation numbers. But how do we define reduction? Reduction is remember oil rig? Of electrons. It's all about who's getting and who's giving away electrons, okay? So reduction is the gain of electrons, and oxidation is losing electrons, okay? That's where you come up with oil rig. Reduction is the gain, oxidation is the loss. And then solubility rules, how to apply them. That kind of ties in with precipitation reactions. And then we're going to practice some redox, because I feel like that's the one. If we're going to practice one of these, we're going to practice that one. Here are the rules for assigning oxidation numbers, because when you're doing a redox reaction, if you're trying to figure out, is this reaction redox or not, you want to see, is anything changing charge, quote charge, or oxidation numbers. So this is what Kennedy was saying. An element by itself has an oxidation number of 0. And then if it's a monatomic ion, you get an oxidation number the same as it would be as its charge, as an anion or a cation. And then in a compound, an atom usually has the same oxidation number it would have were an ion. 2 and 3 are kind of very similar rules. And then 4 is important because the sum of oxidation numbers in a neutral compound is 0. So sometimes it's really hard to assign oxidation numbers because certain things can have really unique oxidation numbers, like they're not going to match their charge. Like sometimes carbon can have an oxidation number, and we know carbon doesn't usually become a cation or anion. So the way this works is if you have something like, what's a good example? SO2. How would I assign oxidation numbers here? Okay, so I'm going to go with what I know first. I know oxygen. Well, let me say this. The first element that is written, usually it will always has the positive oxidation number. Okay, positive oxidation number. The second element is going to have the negative oxidation number, just like if you were writing an ionic compound. You always put the cation first, anion second. So here, I know oxygen is always going to be a -2. Okay, I know that because what does it say? In a compound, an atom usually has the same oxidation number it would have if it were an ion. And oxygen is just one of those atoms that is very predictable. You're not going to see it do weird stuff. So I'm going to assign it with a -2. Okay. Now I have 2 of those in my compound, right? So if I'm trying to apply rule number 4 here, which says it's all got to add up to 0, I got to say -2 times 2, which means this whole negative side comes out to -4. So now I know whatever the sulfur is, it's got a positive oxidation number. It's got to balance this to 0. And if I've got -4 on one side, I know this sulfur has to have an oxidation number of +4. And that's kind of weird. We normally sulfur, because it's in the same group as oxygen, would behave just like oxygen, but here it's different. Okay. And this is an example of how this can sometimes be different. With that, I'll say I'm not going to find the most nuanced problem I can find. Finally, y'all are already going to be stressed out. So they're going to be pretty straightforward ones. We're going to practice them in a second, but I did want to give you an example of how you go through and assign these. So let's do some practice. We have silicon, chlorine makes silicon tetrachloride. So how would you assign oxidation numbers on the reactant side? 0. That's by itself. Chlorine is by itself. Yes, it's a diatomic, but it's still by itself. It's not combined with another element. Now we got to go through just like we did a second ago and assign oxidation numbers to silicon and chlorine, chloride here in this compound. How do we do that? Anybody have an idea? The oxidation numbers, yeah. What would you want to get? I would start with chlorine. Chlorine is another one that's always predictable. -1, yep, and you got 4 of them. So that means if I split this in half and I got the positive side and the negative side, then times 4, this negative side comes out to a total of -4. So now the silicon has to balance that. So it's got to be a +4. All right, so now we got all of our oxidation numbers assigned. The chlorine is a -1. When you're picking what chlorine is, you look at what you originally assigned it, not what you multiplied it by, or not what it totaled up to. What you assigned an individual chlorine, that's its oxidation number on the product side. And then silicon is a +4 there. So we see that silicon is going from 0 on the reactant side, and it's becoming something with a +4. And then chlorine was a 0, and it's becoming a -1. Right, because that's the total of all the chlorines. But what we assigned to chlorine was a -1. Okay, so what's being oxidized and what's being reduced? Yep. So that means silicon's being oxidized. And I'm not going to ask you, so which one was the reducing agent and which one was that? Remember, it was like flip. Just if you can do this, tell me what's oxidized, reduced, then you're good. Okay, you want to do one more? Okay, here. Now go ahead and start working on this one for a second. I'm going to give you a minute. All right, anybody have some answers? Oh, you did the bottom one? Okay. Did everybody else do the middle one? Y'all did the bottom one? Oh, everybody did different ones. Okay. Okay, we'll just do both. Somebody who did the middle one, what'd you give chlorine? 0. What'd you give sodium and bromine? That's right. Okay, over here, what'd you give bromine? And then what'd you give sodium and chlorine? Okay, so what's being oxidized, what's being reduced? So chlorine is going from 0 to -1, so that's reduction. Sodium doesn't change, so I don't really care about sodium here. But bromine is going from -1 to 0, and that's oxidation. Okay, now somebody, Alicia, you're saying what? Did you give? So yes, chlorine here does add up to -3, but an individual chlorine would have a -1. To get it to add up to -3, you did -1 times 3. There you go. And so chlorine starts out as well, some of them are -1, but some of them are 0. So, and then what did you say on the product side? Yeah. Right. There you go. So we go from a +3 to a +5, which is oxidation. And then some chlorines stay a -1 the whole time, but these go from 0 to -1. So there is some reduction happening, although not on every chlorine atom, on some chlorine atoms. So it's still okay to say that's the element that's reduced. Okay. Yeah, you try to find anything that's changing. If something's decreasing in oxidation numbers, that's reduction.
I think that's one of the issues I have with we call septators. Like when something
Isn't
I
changing.
have a hard time when I have a part of the problem that's like I shouldn't be looking at.
Mm.
Mm-hmm. Like I need to figure out ways to like identify something that's unnecessary.
Yeah, theirs comes with time and practice, to be honest. Okay, any other questions on redox before we move on? Okay, there's our solubility rules. So remember, everything's pretty straightforward except for down here. So what all that, just to remind you, these exceptions right here only apply to these anions on that side. And what this means is if these are the cations and they're combined with the anion, so if you have like silver chloride or lead to bromide, this is gonna be, it's an exception, which means it will form a precipitate. It will not be soluble, okay? Thank you, Olivia. And this would form a precipitate. Otherwise, everything here, if you see that it's lining up on this side, like it's got ammonium in it or lithium, doesn't matter what the anion is. There's no exceptions to those compounds, okay? So they're aqueous, which means they're soluble. The exceptions here is when they're gonna be solid. Remember that S doesn't stand for soluble, it stands for solid, which forms a precipitate, okay? And then sulfate has its exceptions too. You'll have that part. All right, that's pretty much it for chapter 5. Chapter 6 was where we introduced the idea of a mole. And we started talking about Avogadro's number, and why that's important is because, you know, molecules are really, really small. And we don't really sometimes comprehend how small they are because you have to express that with these really tiny or gigantic numbers. And it's helpful to be able to convert them to mass and talk about them in terms of mass. That's where we came up with mole mass relationships. 1 mole of any substance is the amount of the substance in grams numerically equal to its formula weight in AMUs. So for example, if you have carbon on the periodic table, we know it's 12.011 AMUs. 1 carbon atom weighs that much. But if we have 12.011 grams of it, that's 1 mole of carbon, okay? And if you have a compound with more than one element, you just have to add up. Multiply by the subscript, the number of that atom in the compound, and then add it all up with all the different elements in the compound. And you all practice calculating molar mass, but we'll do that in a second. Anybody remember Avogadro's number? No. Give it a shot. Somebody saying it? 6 point, okay, we're on the right track. There we go. Yes, it is. I know it is. It's not an equation, so no, you need to know that number. Yeah, memorize that. That's Avogadro's number. So why is that number important? Let me shrink this down so I can actually write just another thing about it. Oh, dang. Whatever. Okay, so that is how many atoms are in a mole. Okay, that's how many items are in a mole. I always relate this to the analogy of the word a dozen. Okay, a dozen stands for 12 items. Usually we use it to talk about eggs, right? Because you purchase eggs per dozen at the store. But it doesn't have to just be eggs. It could be a dozen pennies, a dozen people, a dozen houses, a dozen neighborhoods, right? Same idea with a mole. A mole stands for 6.022 times 10 to the 23rd things. We, in this class, for the sake of this class, are usually applying that to the number of atoms or number of molecules present, okay? But remember in the lab, y'all had that one with the pennies? And so Avogadro's number was that many pennies, okay? 1 mole of pennies would be that many, but we're usually talking about atoms or molecules. Okay, calculating molar mass. So for example, with urea, the only reason I put this one up here is because sometimes things can be complicated when you have parentheses. So here you got to take inventory of all the things you have. You've got carbon, oxygen, nitrogen, and hydrogen. But you have to remember that this 2 multiplies everything in the parentheses by 2. So you do just have 1 carbon and you multiply that by its number on the periodic table. You just have 1 oxygen and you can always just multiply that by a flat 16. Here you would have 2 nitrogens. And so we'd say times 14.007. And then you have 2 times 2 would be 4 hydrogens times 1.008. Okay, and then you would just add that all up. So remember how to calculate molar masses. I mean, y'all been doing that. I think you did it on exam 3 all the way through. I don't think I really had you do it on exam 4, but well, it was exam 2 and exam 3. And then once you know how to do that, you can use, so whatever this totals up to, 12, 16, 28, and 4. What is that? That is 28 and 12 is 40 and 16 is 56 and 4, that should be around 60. Let's just say it's like 60.5. I'm just making up a number here per mole. That's how you write that. Now, because this is relating the number of grams per 1 mole, we can use that as a conversion factor, okay? And that's this next problem here that I recommend. 6.38 is a really good one. Using molar mass to convert between grams and moles. So in this problem here, it says the active ingredient in milk of magnesium and acid is magnesium hydroxide, MgOH2. A typical dose, 1 tablespoon, contains 1.2 grams of magnesium hydroxide. Calculate the molar mass of I've already given that to you at the bottom there, 58.32. Okay, B, the amount of magnesium hydroxide in moles in 1 tablespoon. So it tells you that a typical dose, 1 tablespoon, contains 1.2 grams of magnesium hydroxide. All right. So if we have 1. Oh, and it's asking to do 1 teaspoon. Yikes. So we actually have to, we can't start with the number of grams. We'll use that in a second. So what would we do? There's some relationships here. 1 TBSP, that's a tablespoon, contains 1.2 grams of magnesium hydroxide. Anybody know how many teaspoons are in a tablespoon? Yeah. 3 lowercase TSP, that'll be teaspoon, is equal to 1 tablespoon. And then we have this relationship here, 58.32 grams per 1 mole. So we're trying to get number of moles here. So we want to start with 1 teaspoon, right? It says figure out the number of moles in 1 teaspoon. So I'm going to start with that number and then convert that to moles. So what would I need to do? Yep, use this bottom relationship here. Cancel teaspoons. 3 teaspoon for 1 tablespoon. Okay, teaspoons canceled. Then what? One for every 1 tablespoon, it's 1.2 grams. Now tablespoons cancel. And then what do? We're almost to moles. Here's where we're going to use molar mass as a conversion factor. Look at you, Candace. Huh? That's not true. So here, right here is where we plugged in the molar mass to use it to convert from grams to moles. Okay, so it's just an example of a problem. I think this is a great problem. Several steps here. Oh, I would give that to you. If this were a problem on the exam, I would tell you how many tablespoons, because that's not something I've asked you to memorize. And although I consider it common knowledge because I cook a lot, I don't think everyone knows that, especially guys. No offense. Yeah. Fair enough. Fair enough. Sad. Okay, I'm not going to give any identifiers, but there is a car that I parked next to. And I'm like not trying to look, but I just parked next to them and I just like happened to see in their vehicle, there are Chick-fil-A bags up through their like passenger seat. I'm like, that's disgusting. Like clean out your car. Yeah. There's just Chick-fil-A bags in the floor. There's been like fry containers. Like, I'm like, that is so gross. Reese's wrappers, like this is, they park in faculty parking. I know. Ew is right. Anybody got our answer? Anyways, you would do 1 divided by 3 times 1.2. Did you get it, Carson? Oh, sorry. I didn't know if that was a calculator. You're good. You don't have to do it, but usually people like to calculate it. Okay. Then once we learned how to calculate molar mass, I talked about mole to mole ratio. So now what we just did is a problem that has no chemical reaction in it, right? I just gave you some info. I gave you a compound, but I did not give you a chemical reaction where reactants make products, right? But if I do give you that, oftentimes you're converting something between one reactant and another, or one product to reactant or something, and you have to use a mole to mole ratio, okay? You guys had to do that on exam 4 with the KOH and the H2SO4 problem with the titration, right? So here we're gonna have to do that. We're gonna plug in a molar ratio and you'll have to use molar masses, okay? So these are kind of those 3-step problems that are a little more complicated. So it says zinc metal reacts with hydrochloric acid according to the following equation. It's already balanced for you. How many grams of hydrogen, okay, this right here, are produced if you have 15 grams of zinc? This is the full 3-part problem, okay? You start with grams of zinc. You got to convert to moles of zinc. You use the molar mass to do that. Then you got to convert to moles of hydrogen. Then you got to convert back to, because the question says how many grams of hydrogen, back to grams of hydrogen. So there's 1, 2, 3 steps. And all you're using is molar masses and a mole to mole ratio. Okay. So we'll start with the 15 grams of zinc. Zinc is 65.39. We don't even have to calculate the molar mass. We just pull it off the periodic table. So 69, I said that wrong. 65.39 grams for every 1 mole of zinc. I like to label my zinc here because I'm about to, that was step 1. Step 2 is always the mole to mole ratio. You're going from moles of one thing to moles of something else. Bless you. So then I'm always going to plug in 1 mole of zinc here because I want that to cancel for every 1 mole of H2. So that was step 2, plug in the mole to mole ratio. Last step is you get the molar mass of hydrogen. Here it's a diatomic. This trips people up. So I can't just plug in 1.008. I've got to multiply that by 2, 2.016 grams for every 1 mole. And that was step 3. Notice, wait, I did that wrong, didn't I? I plugged in the grams on bottom. I need to flip that, 2.016 grams for every 1 mole. Notice you divide by the molar mass first, and then the last step is you always multiply by the other molar mass, okay? You don't divide by both. So you do 15 divided by 65.39 times 1 divided by 1, or you can kind of skip that step mathematically, but you have to write it out in the problem because your mole-mole ratio may not always be 1 to 1. And then times 2.016. Anybody have that? Carson, you don't have to do that, sorry. Thank you. Grams, that's fine, of hydrogen. Okay, I love this next question, part B. Is this a redox reaction? If so, what's reduced, what's oxidized? We won't do the reducing and oxidizing agents. What do y'all think? I'll zoom in on it. What oxidation numbers would you assign here? You know, you're looking at everything. So is this like a combination, decomposition, displacement? Single displacement. Yep. This is a metal. This is an ionic compound. So you got your cation and your anion. And look, the metal displaced the hydrogen. So we give this a 0. We give that a 0 because they're by themselves. That's a +1, -1. And this is a +2, -1. So zinc is going from 0 to a +2, right? So is it oxidized or reduced? Yeah, oxidized. And hydrogen is going from a +1 to a 0. So it's reduced.
So whenever I ask, like, is this a redox reaction? Like, the only way to figure that out is to do this kind of stuff, is there an online equation?
Well, single displacement reactions are always redox. Because something's a 0 when it's by itself, and it doesn't have an oxidation number of 0 when it's in a compound. It's got some sort of number that's not 0. So if I ask you what's oxidized and what's reduced, then you got to go in and figure out that. But if I just say, is it redox or not? If it's single displacement, yes. But there's also other reactions, like think about a decomposition reaction where you have AB making A plus B. Here, this would be like could be a +1, -1, +2, -2, but on this side, they're both 0, right? So those are always redox as well. Combination reactions can also be, those 3 in particular are usually almost, I'm not gonna say always, but maybe I could say always redox.
I was just trying to make sure I understood. So on the product side, the CO2 would be a negative. Is that right?
Well, there's 2 of them. Yeah, so you'd say times 2, which is why I gave the zinc a +2 here. Oh, I think this one is a problem. I want y'all to read this and tell me what we got to do. So, says the principal component of kidney stones is calcium oxalate. A kidney stone is recovered from a typical patient, or a kidney stone recovered from a typical patient contains 8.5 times 10 to the power of 20 formula units, which are, it's just a fancy word for molecules. That many molecules of calcium oxalate. How many moles of calcium oxalate are present? What's the mass of the kidney stone in grams? What would you do here? Avogadro's number. If it gives you a number of atoms or molecules, or it's asking you how many atoms or molecules, you have to use Avogadro's number. So you would take the 8.5 times 10 to the 20 molecules. And it's okay. I know there is Avogadro's number. And remember, if you got to plug it in and you're dividing by Avogadro's number, please put it in parentheses, because if not, your calculator won't divide by the 10 to the power 23rd part. It'll only divide by 6.022. There's that many molecules in 1 mole. So you would pause there and get your answer. That would tell you how many moles. And then you would take your number of moles that were your answer that you just calculated up here. And what would you do to get grams? Molar mass. Let's say for every 1 mole, I would calculate the molar mass. I'd plug in, X amount of that many grams, and moles would cancel. Use the molar mass to convert to grams. Questions on that? Is it okay that I'm kind of briefing through this and not plugging in everything?
I mean, that one was rough for me because I wouldn't have thought to use Avogadro's number. I would've
Well,
just said-
here's the red flag. Here's the alarm that should go off in your head. If you see that word in your problem, this many molecules, or how many molecules, or atoms, this many atoms, or how many atoms, you're gonna have to use Avogadro's. Yeah, I won't use the word formula units. This was just a problem from the book that had that word in it. Okay. All right, that's chapter 6. And then chapter 7, energy, reaction rates, equilibrium. Chalier's principle too. So we talked about the law of conservation of energy, and we talked about how we're looking at enthalpy, entropy, Gibbs free energy. And we had to understand how energy works in chemical reactions. So we said when you breaking bonds requires energy, and you always break bonds on the reactant side. And then forming bonds, which you always do on the product side, releases energy. Okay, so any chemical reaction where you have like AB plus CD is gonna make AD plus CB. You're breaking bonds on this side. So we're always investing energy. So there's always a positive enthalpy term here. And we're forming bonds here, forming new bonds, which always releases energy. And if we're releasing, that's viewed as a loss from the standpoint of the chemical reaction or system. And so there's always a negative enthalpy term here. So it just depends which one's bigger as to how your delta H comes out. Remember, we practice calculating delta H's, or at least looking at a delta H and knowing what that means about the reaction. Okay, so calculating delta H, we said was always the enthalpy of the reactant side, which is always going to be your positive term, minus the enthalpy of the product side, which is always going to be your negative term. And whichever one's bigger, well, they're both, this I guess is what's the absolute value of these. They're both positive numbers. They're both numbers of energy, but it's just since we're subtracting it, that's why I wrote that negative there. Okay, we're subtracting that off, so it's always viewed as a loss. So whichever one's bigger will determine the sign of your delta H, whether it's positive or negative. Okay, and that's where, do you remember a endothermic, is that a positive or negative delta H? Yeah, that is endo is a positive delta H overall, which means your HR was bigger than your enthalpy, or your reactant side is bigger than the enthalpy of your product side. The reaction overall absorbed more energy than it released. You have an endothermic reaction. Okay, let me zoom back in up here. We could write in heat or energy or that number, whatever delta H is, as a reactant. Okay, that's for an endothermic. For exothermic, it's the opposite. It's a negative delta H. So that means the enthalpy of the product number when you released energy, because you formed the bonds in the product side, was a bigger value. So overall, the reaction's releasing more energy than it's absorbing. And if that's the case, if you have an exothermic reaction, heat's not a reactant, we'd write it in, I don't really have room, but you'd say plus heat on the product side. Okay.
So on the change in the HR, we have to see product.
Yeah, heat of the reactant side, heat of the product side, or enthalpy of the reactant side, enthalpy of the product side. Okay, when determining a sign of delta H, delta S now, entropy per reaction, what do you consider? Do what? Say that louder. Yes, we're calculating disorder, but what are the things specifically? If I give you a reaction where you have A plus B makes AB, and this is a, oops, this is a solid, and let's say we got to do this. And this is a gas, and this is a gas. What are you going to look at? State of matter. Okay, so whether things are solid, liquids, or gases, why do we look at that? Why do we consider that? Yes, gases are most disordered. So if you're making something that's a gas, the reaction's becoming more disordered. If you have gases that are condensing into a liquid or a solid as your product, then the reaction's becoming less disordered or more ordered. That would be a negative delta S. What else do we consider? Well, you look at the coefficients. This would technically be a 1, right? And this would have 2. So you consider the number of moles. Okay, I'm going to say number of moles of whatever, the gas or the liquid or the solid. Because not every reaction makes gas, right? You could just be dealing with solids all the way across the board, or liquids, or aqueous things. Okay. And then we put all this together, and we get delta G. So what was the equation for delta G? Delta G equals, y'all remember? I'll give you this on your, this is an equation you'll have, so I guess it doesn't matter if you memorize it or not. Delta H, minus the temperature times the delta S. Oh, one other thing, let me skip back up. Remember that for delta H, you're dealing with units of either kilocalories or kilojoules per mole. For the delta S, we had calories or joules per mole Kelvin. And so that's different. Those units are different. The units for delta H are bigger. The units for delta S are smaller. So that's kind of going to lead us into 2 things we check for before we just throw numbers in and calculate delta G. What do we have to first do? Make sure your units for delta S match delta H, okay? So match units of delta S to delta H. So what I mean by that is if I give you calories, okay, if I give you calories per mole Kelvin for your delta S, and I give you kcal for your delta H, you've got to convert calories to kcals, okay? I'm probably not going to mess with giving you joules and then giving you kilocalories, okay? Making you do both. But what's the second thing we got to check for? Or make sure before we just throw numbers in? Yeah, in Kelvin. Often I give it to you in Celsius. So temperature in Kelvin. Okay, so make sure the temperature is in Kelvin.
For the delta S, if they are all like solids or all gases or whatever, don't you just count the number of moles?
Yeah. Yes, if you had a combination reaction, you're becoming more ordered. If you have a decomposition reaction, you're becoming more disordered. Okay, endergonic, exergonic. Once you calculate your delta G, what does that mean? What's an endergonic reaction? Yep, positive delta G, which makes exergonic a negative delta G. Which one is spontaneous or favorable? Yes, this is favorable or spontaneous. And remember, this is always given to you if you have a negative delta H and a positive delta S. These are favorable. You have the opposite, both opposite, positive delta H, negative delta S, that's both unfavorable. You'll always get an endergonic reaction. So it's exothermic and a positive delta S, increasing disorder, that is favorable. Okay. Here was an example problem from this stuff. Following reactions use in industrial synthesis of PVC. It's like pipe, plastic pipe. That's what that polymer can be used for. It can be used for lots of stuff, but is delta S positive or negative for this process? And is the process spontaneous at all temperatures? So let's just focus on A. Is delta S positive or negative?
Really don't.
The amount of disorder in a compound or the reaction. So we have gases on the reactant side and we're making liquids. It's becoming more ordered. So remember, delta S is a measure of disorder. So we're losing disorder because we're becoming more ordered. That's crazy, right? So delta S here is negative. We're becoming more ordered. We're not becoming more disordered. We're becoming less disordered.
So because things like naturally work in order, that means that there's always gonna be existing water, like that's happening.
There's always either an absorption or release of energy, which is heat.
Less water is positive,
Do what?
but it's like disorder, then it's positive.
If it's becoming more disordered, then delta S is positive. It's becoming less disordered, delta S is negative. If disorder is increasing, delta S is positive. That's how I should say it. If disorder is increasing, delta S is positive. If disorder is decreasing, delta S is negative. Here, disorder is decreasing. So delta S is negative. Is this process spontaneous? So we got, and it tells you delta H. So we got a negative delta H. And we have a negative delta S. And remember, our equation for delta G here is we'll have a negative delta H minus the temperature times a negative delta S. So what do you think about this question? Is it spontaneous at all temperatures?
Well, if you're negative minus delta S, then H would have to make it favorable, right?
The only time it's always favorable is when you have a negative delta H and a positive delta S. Okay, that's when it's always exergonic and would be spontaneous at all temperatures. This one, you don't have that. You have a negative delta H, which is favorable, but you have a negative delta S. So because you got this minus sign here out front, it makes this whole term positive T delta S. Okay, so you got a negative delta H plus T delta S now. So it just depends which term is bigger. If this term is bigger, you're going to end up with a positive delta G. If the delta H term is bigger, you'll end up with a negative delta G. So the answer here is no. No. And it depends on what your temperature is. Okay, at really high temperatures, delta S is probably going to be positive. At really low temperatures, delta G would probably be positive. At really low temperatures, delta G would likely be negative. Kennedy.
If we were to have like a question like this on the exam, would we be given like a temperature to plug in, or would we just have to say like without the number for the temperature?
I'm pretty positive you don't have a question like this on the exam. Now, I think, you do need to know how to calculate delta G. You do need to know, that what's favorable and what's not favorable. Like a negative delta H is favorable and a positive delta S is favorable. But I'm like 99.9% positive. There's not a question exactly like this on the exam.
No negative delta H was positive delta S was favorable.
Yeah. Yep, that's favorable.
Is that not what's happening?
No, we have a negative delta S here. Remember, that's what we determined because we got gases and gases making a liquid.
I thought the bottom was for the question, not on the example.
What are you talking about? This right here?
Yeah.
It is. We got negative delta H, negative delta S. What's favorable is negative delta H, positive delta S.
I guess it's because there's a minus sign on the outside of parentheses and there's a minus sign on the inside.
Right, but what we plugged in specifically for delta S was negative. The only time it becomes positive is when you apply this minus sign out front.
So
But before you plug it in,
Okay.
yeah. Okay. That's all delta G, delta H, delta S stuff. Whoa, chapter 7 was big. Now, we're talking about rates. What determines how fast or slow a chemical reaction will occur? This was energy diagram. So remember, we had, this is your delta G on the y-axis, and this is the reaction progress. And so it all has to do, what determines how fast or slow a reaction occurs is whether they have enough energy. So whether they have enough energy to clear the activation energy. And then if they have the right orientation, the molecules hit with the right orientation. Okay, efficient collisions, that's what we said. But the way you draw the energy diagram, labeling activation energy in delta G, you always have some sort of energy level for your reactants. And then you always have some sort of peak. Now from here, the energy diagram can look vastly different. You could have an endergonic reaction where the products are going to be less stable than the reactants. Okay, and this is a positive delta G. The difference between the reactant level and the product level, that's your delta G. Okay, you could also have, I'm just going to draw another one over here. Something like this, where the products are lower in energy than the reactants. And so if we look at the change between reactants and products, from here to here, this is a negative delta G. This one was a positive delta G. So this one would be endergonic. This would be exergonic. Now, which one's faster, which one's slower depends on the activation energy. Here, the activation energy looks about the same. Remember, that is, I'll change colors. That's the amount of energy between the reactant and the peak. Okay, so this right here, this is your activation energy. That slide over here, same idea. You take the peak, walk it over, find the difference between the reactants and that peak. That's your activation energy. And honestly, they look about the same. I wouldn't say here that one's faster or slower. Only if you have a higher activation energy, a larger activation energy, that's going to be a slower reaction. The smaller the activation energy, the faster the reaction goes, because it doesn't need a lot of energy to clear that. So once we kind of understood those things, we said, but you can manipulate rates with temperature or with concentration. Okay, so if you increase the concentration of the reactants, not the products, just the reactants, you'll increase the reaction rate. The more molecules you have, the more they're going to collide, the likelier your chance of making products. We can also increase the temperature. If we increase the temperature, those molecules have more energy and they're moving faster. And they'll hit with more energy and more likely to make products. Or you could add a catalyst. All a catalyst does is, what does a catalyst do? By how? It lowers the activation energy. So if we added a catalyst to this reaction right here, we'd start out at the same spot, but our activation energy would just be lower. Okay, so you see here, it would be a smaller activation energy compared to what I drew in the black. Okay. We're still in chapter 7, equilibrium and Le Chatelier's principle. Those are the last two topics we covered in chapter 7. We're probably going to be done by noon, but if you have to go, since we've been going for an hour, feel free. Okay. So equilibrium is when we say delta G is around 0. And the forward and the reverse reactions are happening at the same rate. That doesn't mean you have equal concentrations of reactants and products. If we have a system at equilibrium, we can write an equation for K, which is our equilibrium constant. And then we can predict whether the forward or the reverse reaction is favorable, whether you got more reactants or products at equilibrium. Remember, K is equal to, and I'll give you this equation, products over reactants. All raised to the power of their coefficient from the balanced chemical reaction. So considering what we just wrote, says for the reaction here, N2O4 makes 2 NO2, the equilibrium concentrations at 25 degrees Celsius are 0.0325 molar and 0.147 molar. What's the value of K? Our reactants or products favored. So you'd say K is equal to the, and everything's a gas, because remember, you don't include liquids or solids. Just things that are gas or things that are aqueous. So we'd say the concentration of NO2 squared, since we got a coefficient of 2, and on the bottom we'd have N2O4. And we just plug their concentrations in. So we'd say that's going to be equal to 0.0325 squared over 0.147. Then we calculate K. Anybody want to do that real quick? It's lunchtime. What happens when you eat early breakfast? I'm not one of those people who can skip breakfast. I do not understand people who can skip breakfast. Anybody got it? 0.072. So what does this mean? K here is way, way smaller than 1, right? Or well, somewhat smaller than 1. So what does that mean? What can you say about equilibrium here? Here, it's the reverse reaction that is favored. You'll have more reactants than products at equilibrium. All right. And if you remember that slide with the arrow and the color coded, that's that. If you're confused on how we arrived at this, that slide on chapter 7 walks you through those conditions and the value of K and what it means. Okay, another good problem to work is 7.59. This is about Le Chatelier's principle, which says when stress is applied to a system at equilibrium, the equilibrium concentrations shift to relieve the stress. So we talked about changes in concentration, changes in temperature, and then changes in pressure or volume. We really don't address volume so much. Volume is opposite to pressure, but we do talk about change in pressure if you have gases in your reaction. So how does all this work? Changes in concentration. Well, if you increase the concentration of, I'll put an R for reactant. So all we can do is mess with either the reactant or the product. Then equilibrium will shift to the product side, to the right. But if we decrease the concentration of a reactant, equilibrium will shift towards that side, towards the reactant side, to the left. Reactants are always written on the left. But you could also talk about products. Let me scoot this up a little bit. What if we increase the concentration of a product? Equilibrium will shift to the reactant side. And if we decrease the concentration of a product, equilibrium will shift towards the product side, towards the thing we're decreasing. Does that shorthand make sense? Because on every reactant you got, or every chemical reaction, you got reactants and products. So, well, I should draw a double arrow, right? It's equilibrium. Okay, what about temperature? Temperature has everything to do with delta H. So if I give you the delta H for the reaction, you can determine whether heat is a reactant or product. For a positive delta H, endothermic, then we know heat is a reactant. But if we have an exothermic reaction, we know that heat, overall, heat's being produced, so it's a product. So then you can just think of it as though you're increasing or decreasing a reactant or product, which is what we just wrote the shifts for, okay? So if you're here increasing temperature, okay, for a positive delta H, if you're increasing, I cannot spell, temp, then equilibrium would shift. Oh, I need to write that. Equilibrium would shift. I can just write the arrow to the product side. If you're decreasing temperature, it'll shift the opposite way. If it's exothermic and we're increasing temperature, then equilibrium will shift to the reactant side. Yeah, this can make your head spin. And if you're decreasing temperature, it just shifts the opposite way. All those things, okay. Pressure, you evaluate the number of moles of gas. So let's say, well, I'm just gonna write this, okay? So first bullet point, if we increase pressure, equilibrium always shifts to the side of the equation with fewer moles of gas, okay? So you look at your reaction, you say, okay, do I have more moles of gas on the reactant side or the product side? It'll be one or the other. If they're the same, like you got 2 moles of gas on both sides, equilibrium won't shift one way or the other. You just say no change. But if you got 2 moles of gas on the reactant side, 1 mole of gas on the product side, then you got more moles of gas on the reactant side. And it's always, if you increase pressure, it'll shift to the side with fewer moles of gas. Okay, so I just can't tell you here, oh, it's gonna shift left or right. It just depends what chemical reaction you're dealing with. But if you decrease pressure, we get the opposite. Equilibrium always shifts to side with more moles of gas. Oh, y'all can't see that. Okay. Okay, that's chapter 7. That's a lot. All right, all we have left is chapter 8 and 9. Anybody need a break? Anybody need to go to the bathroom or anything real quick?
So when this heat can be reacted or product.
Yeah.
That's determined by whether it's in the
Yes.
reactant.
Yep. Okay, almost done. We got how many slides left? Oh gosh. There's chapter 8. And then chapter 9. We have like, oh gosh, chapter 9. Okay, we got a lot of slides left. I know. I always like get worn down at this point. I'm like, let's just quit. Do what? Yeah. Uh-huh. What's the first thing we're gonna do when finals are over? Sleep, drink.
That's probably a healthy thing to say.
I don't know, a glass of wine, they say, can be healthy. Sleep is a good choice.
You should sleep first.
But if you have children, that doesn't. All right. Okay, what did I write here? Gases, liquids, solids, understanding. So the first thing we talked about was when you're going between a gas, liquid, and solid, and these are common transitions we have common names for: melting, freezing, evaporating, condensing. Okay. When matter is changing between state, there is always, it's either always an exothermic or endothermic process. Okay. If you're thawing something out, you're heating that thing up. It's heating up slowly, maybe on its own, but you're taking it out of the freezer to room temperature. You put it at a warmer temperature. Okay. So that would be endothermic. It's absorbing heat so that it can melt. Okay. The substances. If it's freezing, then it's exothermic. Okay. It's releasing heat so that it can freeze itself. Okay. So we looked at intermolecular forces and amount of kinetic energy associated with each state. We said gases. How do I want to write this? I guess. Trying to zoom in. It's like not reading my fingers. Just made it worse. Whoa. Okay. Gases. Do the particles in a gas have high intermolecular forces? Are they interacting a lot or low? Think about a gas. They're moving around, but are they interacting with each other? No, they're not sitting there together like they are in a solid. Okay. So we said gases have low amounts of intermolecular forces, but high kinetic energy, right? We said solids have high amounts of intermolecular forces, low amounts of kinetic energy. Okay. Those are things we talked about. How arrangement energy change when matter undergoes transition. That's what I think I actually talked about this first. Okay. Melting, condensing, sublimation. We said things like melting. That would be like going from a solid to a liquid. So this is going to be absorbing heat. So we'd say that have a positive delta H. We labeled a whole little chart that showed the transitions with positives and negative delta H's. Okay. That's kind of all I want to say about that. But since we brought up intermolecular forces, then we define these three: London dispersion or van der Waals forces. We said these are the weakest, and they occur in all molecules. But we said they're dominant. They're the strongest type of intermolecular force present in nonpolar molecules. Okay, because nonpolar molecules won't have dipole-dipole and they can't hydrogen bond. Dipole-dipole forces are the intermediate when it comes to the strength of the force or the amount of energy associated with it. And we said these are dominant in polar molecules that cannot hydrogen bond. Oops. So if a molecule is polar, but it cannot hydrogen bond, then the strongest intermolecular force present for that molecule would be dipole-dipole interactions. Where you got, remember how this works is if you have some sort of molecule that's got a partial positive region and a partial negative region, they orient themselves with a neighboring molecule the opposite way. Like this. And it's where the partial negatives and the partial positives are close to each other. Hydrogen bonding, these are the strongest. This is the strongest intermolecular force. And what are the requirements? What do you have to be a molecule that can hydrogen bond? Hydrogen, what kind of hydrogen? Water can hydrogen bond, but what do what? Yeah, so you have to have one prerequisite. If you have to have a lone pair on specifically oxygen, nitrogen, or fluorine. The second prerequisite is you have to have a positively polarized hydrogen. I don't know if that looks like a. That is bonded to an oxygen, nitrogen, or fluorine. Okay. When we explained all these, the biggest takeaway is we looked at understanding how these forces influence melting and boiling points. So what I did on the exam is I gave you a couple different kinds of molecules, maybe a non-polar one, a polar one, and one that can hydrogen bond. I said, which one would have the highest melting point? Which would have the highest boiling point? Or vice versa. I could say which one would have the lowest. Okay. The type of intermolecular force holding molecules together, the stronger that is, the more energy it's going to take to melt it or boil it, the higher the boiling point would be. So molecules that can hydrogen bond are going to have the highest melting points and boiling points. Okay, so these tend to have the highest melting point and boiling point. Molecules that can only interact via London dispersion force, so non-polar molecules, those will have the lowest melting points and boiling points. Now, specifically, I remember on exam 3, I gave you 3 molecules. They were all carbohydrates that were varied in size. I think I gave you something like this. I gave you methane, CH4. And then I gave you ethane, which was like C2H6. So those are all hydrogens. And I gave you like propane. These are all hydrogens, okay? So obviously these are all nonpolar molecules. And which one have the highest or highest or lowest boiling point here between those 3? Right, why? No. It all has to do with surface area. This one has a larger surface area. We said the more surface area a molecule has, the more London dispersion forces it could interact with. So Grace, you're not like in a totally wrong ballpark with that answer, but when you say more bonds to break, I think that you're talking about bonds within the molecule, like these bonds. We're not breaking those bonds. We're trying to break interactions between that molecule and a neighboring molecule to boil it. We're just trying to individualize the molecules. That makes sense. So yeah, this one would have the highest boiling point, and this one would have the lowest. Okay, but here you're just comparing nonpolar molecules. This is a positively polarized hydrogen that's bonded to an oxygen, nitrogen, or fluorine. And remember, we call the lone pair is the acceptor. Okay, and this is the donor. So you could simplify it. If I asked you specifically on the exam, you could say they got to have a donor and acceptor. That's kind of the easy way to summarize it. Okay, we're not going to do all these, but I think it's good to let's just take the first 3 here. Could you identify the predominant, meaning the strongest intermolecular force that these molecules would have? So N2, I think the quickest way to do this is draw out the Lewis structure. What kind of molecule is this? You got to be quickly able to decide, is this polar or non-polar? Do what? Non-polar, right? So this would have London dispersion. I'll just abbreviate. London dispersion or van der Waals forces. HCN, you just draw that out. Now, you will have an electronegativity chart, and you might want to refer to that. But I've always told you, you can memorize that hydrogen-carbon bonds are always nonpolar. If you go look at the electronegativity chart, the carbon-nitrogen bond is polar. You can draw that in. So guess what? This has a dipole. It does have a lone pair on a nitrogen, but could it hydrogen bond with itself? No, because it does not have a donor. This carbon or this hydrogen right here is not positively polarized because it's not bonded to an oxygen, nitrogen, fluorine. It's bonded to a carbon. Okay, so this would only have what kind of intermolecular forces? Yes, dipole, dipole. Okay, last one. Actually, instead of doing C, let's do F. So you got to draw this out. And we got a carbon, and the only way these oxygen works out, if you mess with it, is like this. What do you think about a molecule like that? Space really doesn't have, it's not what we're trying to answer here. We're trying to say, is this molecule polar or non-polar? It's polar, okay? Let me highlight all the bonds that are polar. That's a polar bond, that's a polar bond, and that's a polar bond. Okay. Now, So this is polar. We can draw dipoles in. This would actually be bent, this oxygen, so it's gonna look like these dipoles cancel right here, but they don't, because it's bent. And I didn't draw it bent, I drew it linear. So, would you say dipole-dipole interactions are the strongest this could have? No, why? You got donors and acceptors, okay? Every lone pair right here that I'm gonna highlight, these are all acceptors. And this hydrogen right here is positively polarized, so this is a donor. And these are all acceptors. So this can't hydrogen bond. Okay. I think that's not everything in chapter 8. That's half of chapter 8. Oh, guys, I need a break. Y'all do too. If I do, I know y'all do. You want to take a break or do you want to power through? Okay, get it done. All right, then we talked about gases. So we looked at first units of pressure. I will give you, how nice am I? 1 ATM, 760. How many PSI was that? Yep. And 101,325 Pascal. So I'll give you this on the exam on your equation sheet, even though it's technically not an equation. I hope I remember everything I said I would give you. You'll call me out during the final and be like, write this on the board, please. Okay. The combined gas law. So we talked about units of pressure because we were talking about gases, and there's pressure, volume, and temperature. Those are the three variables we look at when we're understanding how gases behave. And those are all modeled in these gas laws. We have the combined gas law and the ideal gas law. Those are the two I want you to focus on. Again, I'm going to give you these equations. Combined gas law is P1 V1 over T1 equals P2 V2 over T2, okay? So here, I just go through and I label, oh, that's a volume, that must be V1. That's a pressure, that must be P1. That is a temperature, must be T1. Here's another temperature, that must be T2. And we got another pressure, that's P2, and it's asking for what is the volume. So I'm looking for V2, all right? Now, before I just plug all this in, what did I have to make sure of? Units, what about them? They have to match. And temperature has to be in Kelvin. Temperature's gotta be in Kelvin, okay? So I convert both my temperatures here, 20 and 0 to Kelvin. It looks like I got ATM for both pressures. I just plug everything in. And I'm solving for V2. Is V2 in the bottom of the equation? So do I have to flip anything? If I do have to flip it, like if I'm solving for T2 instead of V2, what can I do? Flip the whole thing. And what that means is you got to flip both sides. That would become, the equation would become this. Don't just flip one side. Okay. And then you can move things around, get that variable by itself, plug everything in and solve. Yes. So you take your 20 degrees Celsius and you say plus, what's the magic number? 0.15. So it'd be 293.15 Kelvin. And you do that for any temperature. Okay, then you got the ideal gas law. You need to memorize R. You need to memorize, if there's two numbers you memorize R and memorize Avogadro's number. Okay, it's not an equation, so I'm not going to give you R. But I will give you all these pressure conversions. So R is 0.0821, and it's ATM times liters on the top, mole times Kelvin on the bottom. All right. This one, the ideal gas law. Anybody remember what that law is? PV equals nRT. There we go. So here's an example problem. It says if you got 15 grams of CO2 gas, a volume of 0.3 liters and 310 Kelvin, what's its pressure in millimeters mercury? So this one's actually challenging because you got some converting to do. So look, we're gonna rearrange our equation here to get pressure by itself. So I'm gonna divide both sides by V. Oh, no. And what that's gonna leave us with, pressure equals nRT over V. So that's always step one, is rearrange your equation to get the variable you're trying to solve for by itself. Then I need to plug in moles of gas for N, plug in my gas constant for R. I'm gonna plug in this temperature right here for T, and I'm gonna plug that in for V, but I don't have moles. They give me grams. How terrible of them. So we gotta just take this 15 grams of CO2 and convert to moles, which y'all know how to do in your sleep now, okay? CO2, that's 12 and 32, so that'd be like 42 grams per mole. Okay, so you convert that to moles. Whatever that number is what you'll plug in for N. Okay, then you would calculate all this and you get some sort of pressure. So you'd say pressure equals blah, 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 but it'd have units of ATM, okay? And it's asking for it in millimeters of mercury. So the last step there is you would take your answer of pressure in ATM, convert it to millimeters of mercury. Okay. People who are gonna watch the recording of this are gonna be like, what?
You must be on the last step.
So you would plug everything in right here and you would calculate pressure, right? But your units of pressure, since our gas law or our gas constant, I can't zoom in. Look, it has ATM. So that means your answer for pressure is gonna have units of ATM. You just gotta convert it to millimeters of mercury. All right, that's chapter 8. Boom, done. Last one. Solutions. So this is part of what we just took an exam on. So this should be somewhat familiar. Although considering our exam scores. I've got to throw I've got them all graded. I just got to put the numbers in Blackboard. So I'm actually really interested to see. I'm not hopeful.
When we take a picture of our thing filling out online, like not the thing itself, but the, you know, you
The
submit
read
it.
receipt.
Yes.
Yeah.
We just email it to you.
Yeah,
the
just
screenshot.
email me that screenshot or that picture. Okay, solutions. We got solutions are a type of homogeneous mixture. But we also a colloid can be a homogeneous mixture as well. We said the difference was just particle size. Solutions have smaller particles than colloids. Solutions are translucent, not opaque. Okay, you can see through a solution. Salt water. Not thinking about it, the atmosphere, okay? But you can't see through a solution of milk. You can't see through, I mean, those other examples I gave you on exam 4, blood, paint, things like that. You can't see through those.
I did get tripped up because I don't know if I drink different grape juice than you,
The white grape juice.
but I can see through it. So does it need to be clear or does it need to be?
Yeah, but grape juice has sugar in it. Sugar is a large biological molecule. Okay, proteins, fats, sugars, those kinds of biological molecules are way bigger than what a solution, standard solution definition. Okay, so then we said there's 2 parts of a solution. You've got the solute, which is what is being dissolved. And we got the solvent, okay, which is what you're dissolving your solute into. Is dissolved in the solvent. Okay. And it doesn't just have to be a liquid. Okay. You can have solutions of gases mixed in gases. The solvent is present in greater amount. Solute is in lesser amount. Okay, how do we know if something will be soluble or not? This is where we discuss the phrase like dissolves like, which has everything to do with those intermolecular forces we just discussed. Okay, if the solute is held together by hydrogen bonding forces and the solvent is held together by hydrogen bonding forces, those things are going to be soluble. But if you got a nonpolar molecule as your solute and a polar substance as your solvent, they will not mix. They will not be soluble. Okay.
So what do you just find
You can do that as well. Yeah. Okay, effects of temperature on solubility. We said solids become more soluble in a liquid as temperature increases. We said gases become less soluble in a liquid as temperature increases. And so again, this is in a liquid. Both things are, your liquid is your solvent there. You can't say these rules apply if you're trying to dissolve something in a gas or something else. We also talked about Henry's law, which was gas solubility increases as pressure increases. So gas solubility and pressure are proportional. This is the equation you'll have for Henry's law, C1 over P1 equals C2 over P2. Remember that units for C, okay, they're units of X amount of grams per 100 milliliters, and you don't divide by that 100. That's just part of the unit. Okay.
What did you just say?
For C, we have a variable C here, C1 over P1 equals C2 over P2. C has units of grams per 100 milliliter.
Oh, but it's just like R, it's just like.
You just keep this 100 as part of the unit. You don't divide by 100 when you're calculating an answer for that or with that. There's a great Henry's law problem. The review slides that I sent out right before exam 4, I meant to send them the day before, but I sent them out the day of. There's a great practice Henry's law problem, and there might be some in the textbook as well if you want to practice that. Okay. Then the last big hitters in chapter 9 were this weight, volume, percent, and molarity. And I think, okay, 3 slides left. Weight, volume, percent. So let's just practice an equation for that. It says the concentration of glucose in blood is approximately 90 milligram per 100 ml. So 90 milligram of glucose per 100 milliliters of blood. What is the mass, volume, percent concentration of glucose? What's the molarity? So what is our equation for weight, volume, percent? Anybody remember? Uh-huh. Yep, milliliters of solution times 100. Okay, so here our solid is glucose being dissolved in blood, which is the solution. So we need grams and we already have milliliters. So we're going to take the 90 milligrams of glucose. I'll use a capital G for glucose. And I'm going to convert that to grams. I know there is 1,000 milligrams in 1 gram. So say I got 0.09 grams of capital G glucose. And that's per 100 milliliters of blood. So now I can just plug all this in. So my weight, volume, percent is going to be equal to 0.09 grams divided by 100 milliliters, and then you go times 100. And honestly, you don't even have to plug this in the calculator. You can see that the hundreds cancel. So my percent is just 0.09%. But then it asks for what the molarity of glucose is. So here, what is molarity? Molarity is equal to moles of solute over liters of solution, and you don't times it by anything. So we need moles of glucose. We need liters of solution. So I would take this 0.09 grams and I'm going to convert it to moles. You need the molar mass. I would probably give you the molar mass. It's 180.156 grams per 1 mole. So that would give us 0.09 divided by 180, 0.09 divided by 180.156. We would have 0.0005 moles. And 100 milliliters. We need to take this 100 milliliters up here and convert it to liters, right? There's 1,000 milliliters per 1 liter. So you should get 0.1 liters. So you do 0.0005 divided by 0.1 liters. And you'll get 0.005 molar, okay?
Okay, so did you take the molar mass and then times by the grams that we have?
I took the number of grams from the first part. We converted the 90 milligrams. The problem originally gives us, so we converted that to grams. I divided by the molar mass. Yeah, 180. And got moles. It was 0.005 moles. I just divided that by the number of liters. All right. And then the last thing we did with molarity is we use it as a conversion factor. This is if you're given a chemical reaction, reactants and products. Otherwise, well, there's other problems too, but mainly think on the final, you'll use this as a conversion factor with a chemical reaction. So 9.6 is a great problem from the textbook. It says sodium thiosulfate, the major component in, was this a homework problem on mastering? Maybe you don't remember. The major component in photographic fixer solution, which is totally obsolete now, I'm sure. We don't have to do all they used to do to develop pictures. Reacts with silver bromide to dissolve it according to the following reaction. How many moles of sodium thiosulfate would be required to completely or react completely with 0.45 grams of silver bromide? All right. So we're given the number of grams of silver bromide. That's where we need to start. 0.45 grams of AgBr. And we're trying to figure out how many moles of sodium thiosulfate this is. So all we're going to do is first convert from grams of silver bromide to moles of silver bromide. This is using the molar mass of silver bromide. Then we're going to plug in a mole to mole ratio and convert from moles of silver bromide to moles of the sodium thiosulfate. So we'll plug in our mole to mole ratio, which if you look at the reaction, it's 1 to 2. So for every 1 mole of silver bromide, it's 2. So we just need the molar mass of silver bromide, which I don't want to calculate. So I'm just going to Google it. Oh, what's molar mass? It's 187.77 for 1 mole. So you would do 0.45 divided by the 187.77 times 2. And you would find that it's 0.004. Whoops, I wrote a 7. 48 moles. Then part B, this is where you're going to use molarity as a conversion factor. How many milliliters of 0.02 molar sodium thiosulfate solution contain this number of moles? All right, so we have 0.0048 moles, and we're trying to convert to milliliters. Molarity, with the 0.02 molar is this. It's 0.02 moles per liter, right? That is molarity. You can rewrite it as mole per liter. So I'm going to plug that in right here. I want moles to cancel, so I'll just flip it upside down per 1 liter. Moles will cancel, and then I'll just convert all the way to milliliters. 1 liter is 1,000 milliliters. So take this number, divide by 0.02 times by 1,000, and you would find that it's 239.65 milliliters. So this right here is where I'm plugging in my molarity as a conversion factor to convert from moles to liters. Okay. Last slide, and we're done. Dilutions, electrolytes, osmosis. Those are kind of the last little topics in chapter 9. Dilutions, you just have that equation. All that this is I give you 3 of the 4 variables and you solve for the 4th. Okay. So I'm not going to work 100 problems on that, or even 1. Electrolytes. You guys remember? I actually don't think I put an exact question about electrolytes on here on exam 4, but you can have strong electrolytes, you can have weak electrolytes, or you can have what we call non-electrolytes. So strong electrolytes completely ionize. Okay, that would be something like a strong acid, an ionic compound. And in those, so if you have like HCl, it will completely ionize into H plus and Cl minus, okay? So you just got one-way arrow there. A weak electrolyte partially ionizes or partially dissociates. A weak acid would be an example of that. So acetic acid is the first one I think of, CH3COOH. That will, you get a double arrow, can partially ionize into H plus and acetate. I don't know if y'all can see that very well. Non-electrolytes don't ionize. This is molecules like sucrose, insulin, kind of more biological molecules that could dissolve, but they're not going to break up into ions. Osmosis and osmolarity. The biggest thing there is we talked about a gradient. Okay. We said osmosis happens because there are gradients, which you have a high concentration of your solute and a low concentration of your solute separated by a semi-permeable membrane. And we said it is the movement of solvent that works to create isotonic solutions. Anybody remember what the word isotonic means? Same osmolarity. Okay. And remember, osmolarity is just the number of particles. I'll give this equation to you, equals number of moles of particles per liter of solution. So it's very much like a molarity, but you're considering the number of particles. You had a problem like this. It was worth a lot of points on exam 4. You had to calculate osmolarity of 2 solutions and compare them. So something with a higher osmolarity is hypertonic. Something with a lower osmolarity is hypotonic. So this is a great question that kind of hits on osmosis, osmolarity. Why do red blood cells swell up and bust when placed in pure water? Thoughts? Straw beaker.
They suck the water and stuff.
Here is our red blood cell. What? They suck the water in. Why? So if this is our red blood cell, and this is just pure water in the beaker, what do we know about the red blood cells? It's going to have, I shouldn't draw X's, I'll just draw little dots. It's got a lot of particles. It's got salt, sugar, you've got electrolytes in your blood, all kinds of particles. The water has no electrolytes. So all the water, because you got a hypertonic inside the red blood cell, it's the solvent that moves, the water is going to rush into the red blood cell, causing it to bust eventually. Because you got, this is a hypotonic solution, and this is hypertonic in here.
Is that why they can't just give you straight up water when you're getting on the